Now we are going to derive the second result in the mirror equations. That is, how does the size of image compares with the size of the object. So the definition of the magnification M is the h naught, the height of image, divided by the h naught. So we find out actually this ratio can be rewritten in terms of the di and d naught. So this is the relation we have here. So hi divided by the h naught is simply the negative of the di divided by d naught. So this is how we get this relation here. So now in the future you can decide that if the virtual image they are always bigger, then the ratio will be bigger than 1. So which means the image is magnified. Also, the virtual image is always upright. So they are always positive. So magnification is positive. But it could be negative. So now let's try to summarize how the result and teach you how to use the mirror equations carefully. The reason is because the h naught, hi, d naught, di, the value could be positive or negative. It depends on if it's a concave or convex mirrors. So if you have the concave mirror, then the f is always positive. The reason is because the focal point is always in front of the concave mirror. But the focal length is negative for the convex, and the answer is very trivial because the focal point is always behind the convex mirror. And how about the magnification M? So M is always positive for the upright image. The reason is because for the upright image, h naught is always positive, and hi is always positive, and h naught is also positive. So M is positive. But now, if it is for real image, h naught is positive, but hi will be inverted, so it is negative. So that's the reason that M is negative for the inverted image. Now let's try to think about in terms of the image distance. The di is positive for the image in front of mirror. So if it is formed in front of mirror, so this is most of the time, I would say this is for the concave. For convex, you cannot form a real image. However, you can also form a virtual image for the concave. Yeah? So in that case, if you form a virtual image, no matter it is concave or convex, the di is negative. It is because the image was behind the mirror. So di is negative. Please be very careful about the sign here. And finally, the object distance. So since the object distance is positive if you put them in front of mirror, so that should be not a surprise. And it will be negative if you put it behind the mirror. So for most of the time, d naught will be positive, unless in the very special case, it is put behind the mirror. So you will find out that the sign is determined whether the position of the focal point or the image or the object is in front or on the back of the mirror. Then you can determine the sign appropriately. So now let me give you examples. So there's a Santa Claus come to your house and give you a present. And because you have the own ornament on the trees and the Santa Claus can see his own image. So the question is that you can treat the ornament as a convex mirror. And the diameter of the sphere is given, and the distance between the Santa Claus to the mirror is also given. So this is actually your DO. And this is the R value. But this is 2 times R. Yeah? And we wanted to know is that what is the location and the size of the Santa Claus image. Assume the Santa Claus height is 1.75. So this is the UH naught. So you have H naught, D naught, and this is 2 times R. So therefore, in order to find out the position and the size of image, let's try to find out the focal length first. So how do we find out the focal length? So this is a convex one. Yeah? So now focal length is -1/2 of the radius. And what is the radius? It is 4.52, which is half of the value. So therefore now you can calculate your focal length is the negative 0.0226. And why you need to find out the focal length? It is because you want to find out the position, the location of the image. So you can use the mirror equations to get it. So from the mirror equation, you know that 1 over di is 1 over f minus 1 over d naught. And now you got the focal length. So you can calculate that now. The distance of the image to the mirror is negative 0.022, which is the behind the mirror. And now if you already know the d naught and the di, so now you can calculate the m value, the magnification. So what is the magnification? It is a negative of di divided by d naught. But be careful now, di is negative. It is behind the mirror. So therefore the m is 0.05254. So from this value, now you can calculate using the second equation or mirror equation. The height of the image is m times h naught, which is 0.447 meter. So definitely the image is much smaller now. So now let's take a look about the second conceptual quiz today. So be careful, it is a plane mirror. So the answer is C. And why both A and B? So for sure, for the plane mirror, the distance from the image to the mirror is 2. So therefore, the distance from the image to you is 2 plus 2. So it is 4. So the answer is C. So if no questions, now let's try to study the second topic. It is the refraction of the light. So here it is a different case. All the previous scenario is about the mirrors. So the light is reflected. So which means the light cannot really penetrate through the mirror. The light is always reflected. So all the image formed behind the mirror is through the dashed line, which is a virtual light. But the refraction of light is different. Even you have some material there, the light still can penetrate through the material. But the penetration is no longer smoothly because you can see between the layer you have material 1 and 2, so it is made of different kind of material. So what happens in real life is that when the light moving in the material 1, when they try to enter into the material 2 without being reflected, what will happen is that they will travel at a different speed in material 1 and 2. And the change of the speed will cause the ray to bend. So let me give you a trivial explanations. So in the material 1, with the same time period, they moving at the velocity v1. So the total distance traveled is v1 multiplied by delta t. However, if you enter into the material 2, now it is moving at a different speed. So now within the same period of time, the distance you are going to travel is v2 multiplied by delta t, which means the distance traveled is no longer the same. So therefore, if you travel at a different length, the angle for the triangle will be different. So the direction of light will be bended. So this is just one of the examples. So we define the incident angle is theta 1. So theta 1 is the angle compared with the normal line. And the theta 2 is the reflected light compared with normal line also. But now theta 1 and theta 2 are no longer the same because this is not the law of the reflection anymore. And now for the reflected light, the theta 1 and theta 2, actually there's a connection in between them. And the connection is the so-called Snell's laws. So from the previous slide, the angle of the reflection theta 1 can be related to theta 2 through this connection. So why this is true? So now we should go back to the previous slide. We should use the triangle we just derived. So let's look at the first triangle here. So what is the sine theta 1? Sine theta 1 is the V1 delta t divided by AB. Agree? This is sine theta 1. And what is the sine theta 2? Sine theta 2 is V2 delta t divided by AB. But did you notice that from this true triangle, they share the same AB? So from that relation, because the AB is the same, then you can get this result. Now, if the sine theta 1 divided by V1 is the same as this one, it seems that is enough, yeah? But we find out we have to define a quantity which is called the index of the refraction, which is related to the material, N. So because we have different kind of material in layer above for the layer 1 and layer 2. So we are going to define the index of refraction for that particular material N, which is velocity moving in that material is no longer the same. Even it is a light, but it is not going to move at the speed of light. Instead, they are going to move slower. So the index of reflection of that material is all bigger than 1. So C divided by value bigger than 1, this value is more than the speed of light. So this explains why that the velocity will be changed when they go entering to different kind of material. So now, if you try to define the velocity of the speed of light in that material is C divided by N. Now it can rewrite this formula in terms of this. This is the N1 multiplied by sine theta 1 equal to N2 multiplied by the sine theta 2. So now you can relate it to that how strongly the light will be reflected depending on the material. So for example, if you have the light incident from the air to the water, so the original incident light has an angle 60, so theta 1 is 60. So we know that water is more dense than the air, so N2 will be bigger than N1. So if N2 is bigger than N1, not a surprise to you that the theta 2 now should be smaller. So now, if you use the information given here, this is the index of the reflection for different kind of substance. So for example, for the air, you can basically treat them like 1. But if you have the water, it is 1.33. So if you substitute the number here, 1 for N1 and N2 for 1.33, you will get the angle now will be theta 2 will be 40.6. But if you now change the material from the water to the diamond, then the coefficient will be even much bigger. It is 2.42. It is more dense, yeah? So if you substitute them N2 into these equations, then you will find out the light will even bend it more toward to the normal lines. So this is the so-called law of the refractions, or sometimes people call them the Snell's laws. So now let's take a look about our final conceptual quiz today. So you have two parallel light close to the interface from air to some material. You have no idea about the material 1 and 2. So based on how the refracted light is bended, could you determine that in which of the media the light traveling faster? So just give you a hint now. So this is how the light is bended. It depends on the density. And now the density is related to the speed of light in that material. Okay? So now the answer is A. Because the bigger the density of the material, the stronger the light will be bended toward to the normal lines. And if it is more dense, which means the light is moving slower in that material. It is more dense, yeah? So which means this value is bigger. So the velocity moving, traveling in that material is slower. So that is the reason the answer is A, 1, because the material is less bended.